Close your eyes for a moment. Feel the ground beneath you. Solid, still, safe. It is lying to you. Right now, the planet you are resting on is spinning faster than it has in 50 years. Days are quietly getting shorter. Atomic clocks, the most accurate instruments humanity has ever built, are losing sync with the ground they sit on. Scientists confirmed it, satellites measured it, and nobody fully understands why. Deep beneath where you are lying, 3,000 miles down, in absolute darkness and heat that melts iron like candle wax, something changed direction. The solid heart of this planet, a sphere of iron the size of the moon, appears to have slowed, stopped, and begun spinning the other way. Above it, the magnetic shield protecting every living thing on Earth is quietly developing a wound the size of an ocean, and the ice holding the world in balance is disappearing faster than anyone predicted. These are not theories. These are measurements, and they are all happening simultaneously, right now, beneath the bed you are lying in. Tonight, we go all the way down, through the ice, through the oceans, through 3,000 miles of rock and liquid iron, to the beating heart of a restless world. If this channel deserves a place in your nights, like this video and subscribe. Now sink in. We begin. There is a date most people have never heard of. June 29th, 2022. Nothing dramatic appeared in the news that morning. No earthquake shook the ground. No storm darkened the sky. The sun rose the way it always does, and the world carried on with its ordinary business. But deep inside laboratories, where the most precise instruments on Earth quietly measure the spin of the planet itself, something extraordinary showed up in the data. Earth finished one full turn faster than it ever had before. The day was shorter than normal by 1.59 milliseconds, less than the blink of an eye, less than the time it takes a hummingbird to beat its wings once. And yet, for a planet that weighs 6,000 trillion kilograms and has been spinning for 4.5 billion years, shaving even that tiny sliver off its daily rotation is like watching an oil tanker suddenly change direction in the middle of the ocean. It should not happen easily. It should not happen without a powerful reason. And the reasons, as it turns out, reach far deeper than anyone first expected. To understand what a shorter day really means, imagine something simple. Picture the Earth as a giant spinning top. It has been turning since the moment it formed from dust and gas orbiting a young star. Every single day you have ever lived, every sunrise, every sunset, every slow drift from light into darkness, what has been one complete turn of that top. We call it 24 hours. But here is something most people never learn. 24 hours is not exact. It never was. The length of a day has always been shifting. Sometimes a little longer, sometimes a little shorter, depending on forces pushing and pulling at the planet from the inside and the outside. For most of Earth's long history, the direction was clear. Days were getting longer. The planet was gradually slowing down, like a top that is running out of energy, turning a tiny bit more slowly with every passing age. The reason for that slowdown is beautiful and ancient: the moon. Our closest companion in space does more than glow in the night sky. It pulls on Earth's oceans with its gravity, raising tides that sweep across the surface twice a day. Those tides are not free. They create friction. The water dragging against the ocean floor and the coastlines acts like a gentle brake on the spinning planet. Millisecond by millisecond, century by century. The moon has been slowing Earth down for billions of years. The effect is tiny in any single lifetime, but across deep time, it adds up to something astonishing. scientists studying ancient coral fossils from roughly 400 million years ago discovered that those corals recorded about 400 growth rings per year, instead of the 365 we see today. Since a year is always the same length, determined by the orbit around the Sun, more days in a year means each day was shorter. Earth was spinning faster back then. Days lasted only about 21.5 hours. The planet has been losing speed ever since, yet it pulled slowly, steadily backward by the patient gravity of the Moon. That slow and ancient deceleration is the expected story. It is the baseline, the steady, predictable direction of travel that every model of Earth's rotation was built around, which is exactly why the data that began appearing around 2016 made researchers stop and look twice. The trend reversed. Earth started speeding up, not in a sudden jolt, not in a way that would knock you off your feet or rattle the dishes in your kitchen, but in a way that the most sensitive instruments on the planet could clearly detect. Year after year, the average length of a day was getting shorter. The numbers were small, fractions of milliseconds, but they were consistent. They were not random noise. They were a signal, and the signal was growing. By 2020, Earth had logged some of the shortest days ever recorded with modern instruments. And then 2021 came in shorter still. And then 2022 delivered June 29th, the fastest single day in the entire history of precise timekeeping. The record did not come out of nowhere. It was the peak of a trend that had been building for 6 years, a trend that ran directly against the direction Earth had been moving for hundreds of millions of years. Something was pushing the planet forward, pushing it hard enough to overcome the ancient drag of the Moon itself. Here is where the mystery deepens. When scientists looked at the data and subtracted every known cause of rotation change, the seasonal shifts in the atmosphere, the movement of ocean currents, the redistribution of water between land and sea, a leftover signal remained, an acceleration that could not be fully explained by any single familiar force. The usual suspects were all still operating. The Moon was still pulling. The tides were still dragging. The atmosphere was still shifting mass from one latitude to another with the seasons. All of those effects were accounted for in the calculations, and yet, after every known factor was removed from the equation, the planet was still speeding up. Something else was at work, something the models had not predicted. The scientific community responded the way it always does when something unexpected appears. They checked the instruments. They cross-referenced data from atomic clock networks in different countries on different continents. The International Earth Rotation and Reference System Service, the global authority responsible for monitoring the planet's spin, ran every verification they had. The instruments were fine, the clocks were accurate, the signal was real. There is a fringe idea, not widely accepted but whispered about in certain corners of geophysics, that Earth's rotation may respond to cycles we have not yet identified. Cycles buried so deep in the interaction between the planet's layers that they operate on timescales longer than our instruments have existed. Some researchers have speculated about resonance effects between the mantle and the core, slow oscillations of angular momentum that take decades or even centuries to complete one full swing. If such a cycle exists, we might be riding the upswing right now, and without knowing when the peak will come or how far the acceleration will go. And that is the open question that hangs over all of this. Is the current speed-up a temporary fluctuation, a brief wobble in a system that will soon settle back to its ancient rhythm of slowing down? Or is it the beginning of something more lasting, driven by changes deep inside the planet that are fundamentally different from anything in the modern record? the scientific community is genuinely divided. Some researchers point to the long history of small oscillations and argue that this is simply a natural variation near the high end of its range. Others look at the number of systems changing at the same time and see something that does not fit neatly into the category of normal variation. What no one disputes is this: the planet beneath you is not turning the way it was turning a decade ago. The clocks built to measure time with perfect accuracy are now drifting out of step with the ground they sit on. And the forces responsible for that drift are not simple. They reach from the thin shell of ice at the poles to the unimaginable heat and pressure at the center of the world. The first clue to understanding how we even notice this acceleration lies in the strangest clock ever built. A clock that does not tick with gears or springs, but with the vibration of a single atom, counted 9 billion times every second. And what that clock revealed about the planet it was sitting on changed everything. Before 1955, the best clocks in the world were mechanical marvels, pendulums swinging in sealed chambers, quartz crystals vibrating inside brass housings. They were beautiful, they were precise, and the finest among them lost or gained about 1 second every 300 years. For daily life, that kind of accuracy is extraordinary. You could set one of those clocks on the day you were born, and it would still be nearly perfect on the day you died. But for measuring a planet, for catching the tiny wobbles and surges in the spin of a world that weighs more than any number your mind can hold, 300 years per second of drift was like trying to weigh a grain of sand on a bathroom scale. The instrument was not sensitive enough. The truth was hiding inside margins too small to see. Then, physicists did something remarkable. They stopped building clocks from gears and crystals. They built one from an atom. The idea behind an atomic clock is strange and wonderful. Every atom of the same element, everywhere in the universe, vibrates at exactly the same frequency. Not approximately, not close enough, exactly. A cesium atom in a laboratory in London vibrates at the same rate as a cesium atom on the far side of the galaxy. This is not a guess or an estimate. It is one of the most tested facts in all of physics. The frequency never changes. It does not speed up when the atom gets warm. It does not slow down when the atom gets cold. It is locked into the deepest architecture of nature itself, as constant as anything we have ever found. Cesium-133, the specific type of atom used in the most precise atomic clocks, vibrates exactly 9,192,631,770 times per second. Scientists took that number and made it the official definition of 1 second. Not the swing of a pendulum, not a fraction of the Earth's orbit around the Sun. The vibration of a single type of atom, counted over 9 billion times in the span of a heartbeat. The result was a clock so steady, so impossibly accurate, that it would not gain or lose a single second in 300 million years. 300 million, not 300. The leap in precision was like going from a magnifying glass to the most powerful telescope ever built. Suddenly, scientists could see things that had always been invisible. And the first thing they saw when they pointed this extraordinary instrument at the planet beneath it was a mess. Earth's rotation, which everyone had assumed was smooth and steady like a well-made wheel, turned out to be full of tiny stutters, surges, and hesitations. The planet sped up slightly during winter in the northern hemisphere, when atmospheric mass shifted toward the poles. It slowed down slightly in summer, when the air spread back toward the equator. Earthquakes jolted the spin by microscopic amounts. Major storms pushed against the rotating surface like a hand pressing against a spinning basketball. El Niño events, changes in ocean currents, even the weight of snow piling up in Siberia. All left faint fingerprints in the rotation data that only an atomic clock could detect. Picture it this way. Imagine you have always listened to your favorite song on ordinary speakers. The melody sounds clean and familiar. Then, one day, someone hands you the finest headphones ever made, and you hear the same song again. Suddenly, there are sounds you never noticed, a faint hum in the background, a slight tremor in the singer's voice during the second verse, a rhythm that drifts by a fraction of a beat in the final chorus. The song has not changed. Your ability to hear it has changed. That is what atomic clocks did for our understanding of Earth. They let us hear the planet's hidden music for the first time. And some of the notes were not where they were supposed to be. For decades, this hidden complexity was manageable. Researchers catalogued the seasonal variations. They measured the effects of earthquakes and storms. They built models that predicted how much the rotation would fluctuate in any given year. And those models worked well enough to keep everything running smoothly. The atomic clocks sat in their laboratories, counting cesium vibrations with tireless patience, and the planet turned beneath them in patterns that, while messy, were at least familiar. Then, the data from 2016 onward began to look different. The usual fluctuations were still there, the seasonal breathing, the storm-driven nudges, the faint pulse of ocean currents shifting weight from one basin to another. But underneath all of that noise, a new signal was emerging. The average length of a day was shrinking, not as a random jump that would correct itself in a few months, as a trend. Year after year, the numbers moved in one direction. The planet was accelerating, and the acceleration was steady enough to separate from the background noise with confidence. Researchers did what researchers do. They checked every possible source of error. They compared readings from atomic clock networks in the United States, Germany, Japan, France, and dozens of other countries. They cross-referenced the clock data with measurements from radio telescopes pointed at distant quasars, objects so far away that they appear perfectly fixed in space, providing an absolute reference frame against which Earth's spin can be measured with extraordinary precision. Everything agreed. The clocks were right. The quasars confirmed it. Earth was genuinely turning faster. Here is something curious that lives at the edges of this field. A small number of researchers have raised the question of whether the atomic definition of a second itself might contain assumptions that could shift over cosmological time. If the fundamental constants of physics, the values that govern how atoms vibrate, were to drift by truly tiny amounts over billions of years, the clocks would never know. They would still count the same number of vibrations, but the second those vibrations define might not mean quite the same thing. It meant 1 billion years ago. This idea is not mainstream. Most physicists consider the fundamental constants to be truly constant, but the question has been formally posed in peer-reviewed literature, and it has not been conclusively closed. It is one of those quiet, unsettling what-ifs that sits in the background of precision measurement, like a shadow you can never quite bring into focus. What the scientific community does agree on is that within the framework of physics as we understand it today, the atomic clocks are right, and the planet has changed. The instruments did not drift. The ground beneath them did. And the gap between atomic time and Earth time, between the perfect rhythm of vibrating cesium and the imperfect rhythm of a spinning world, began to grow in a direction that nobody had planned for. For 50 years, that gap had always grown in one direction. The planet slowed, the clocks ran ahead, and a simple, elegant system was invented to keep the two from drifting too far apart. A tiny patch applied to the fabric of time itself. 1 extra second inserted into the official clock whenever the gap grew large enough to matter. It was a small fix for a simple problem, and for decades it worked beautifully. But the problem is no longer simple. The planet is no longer slowing, and the fix that kept everything together for half a century is now becoming one of the most dangerous decisions in the history of global technology. That decision, and the single second that could crash the systems the world depends on, is where this story takes its sharpest turn. In 1972, the world quietly agreed on something that sounds almost absurd when you say it out loud. Every now and then, we would add 1 extra second to time. Not to a local clock in one city. Not to the watch on one person's wrist. To all of time. Every clock, every system, every timestamp on Earth would pause for 1 additional heartbeat. And then the world would carry on as if nothing had happened. The reason was the gap we just described. Atomic clocks, counting cesium vibrations with perfect patience, kept flawless time. The planet beneath them did not. Earth was gradually slowing down, dragged by the moon's tidal pull, and that meant the planet's version of a day was slowly growing longer than the atomic version. Left alone, the two would drift further and further apart. Eventually, noon on the atomic clock would arrive while the sun was still climbing toward its highest point. Not next year. Not in your lifetime. But across centuries, the mismatch would become impossible to ignore. The leap second was the solution. Simple, elegant, almost poetic in its modesty. Whenever the gap between atomic time and Earth time grew to roughly 9/10 of a second, the international authorities who oversee timekeeping would announce a correction. At the end of a designated day, usually June 30th or December 31st, clocks around the world would count an extra second. Instead of jumping from 23 hours, 59 minutes, and 59 seconds straight to midnight, they would pass through a moment that does not normally exist. 23 hours, 59 minutes, and 60 seconds. 1 extra tick. 1 tiny patch sewn into the fabric of global time. Then midnight would arrive, and the world would move on. 27 times since 1972, this has happened. 27 extra seconds have been stitched into the timeline of human civilization. Each one nudged atomic time back into alignment with the turning of the planet. Each one was a small act of maintenance, like adjusting the hands of a grandfather clock that runs a little fast. And for decades, the system worked well enough that most people never knew it existed. But elegant as it sounds, the leap second was always a headache for the machines. Computers do not like surprises in time. A minute is supposed to have 60 seconds. Always. Without exception, and every operating system, every database, every server that processes information is built around that assumption. When you tell a computer that this particular minute has 61 seconds, some handle it gracefully, others do not. In 2012, a single positive leap second, 1 extra second added to the clock, crashed servers at Reddit, LinkedIn, and Qantas Airlines simultaneously. Engineers spent hours tracing the problem. The cause was not a virus, not a hardware failure, not a cyber attack. It was 1 second. 1 additional tick that interacted badly with the software responsible for scheduling processes inside those systems. Thousands of tasks that were supposed to run in sequence suddenly collided, and the servers froze. That was a positive leap second. Time moving forward, adding something. The software stumbled, but the logic was at least understandable. A minute had 61 seconds instead of 60. Awkward, but conceptually simple. Now imagine the opposite. Imagine subtracting a second. Imagine telling every computer system on Earth that this particular minute has only 59 seconds, that 23 hours, 59 minutes, and 59 seconds simply does not exist. It is skipped. The clock jumps from 58 directly to midnight, and one moment that every system expected to encounter simply vanishes from the timeline. This is called a negative leap second, and it has never been done, not once in the entire history of modern timekeeping. The reason it was never needed is the reason we have been tracing through this story. The planet was always slowing down. Atomic clocks always ran ahead of Earth. The fix was always to add time, to slow the clocks down by 1 second to let the planet catch up. The direction was always the same. The patch always went in the same way. Now the planet is speeding up. The atomic clocks are falling behind. And for the first time since the system was invented, the conversation has shifted from adding a second to removing one. Engineers at Meta, the company that runs Facebook and Instagram, published a detailed paper describing what a negative leap second could do to global digital infrastructure. They did not use gentle language. They called it an event with a potentially devastating effect on software that relies on timers or schedulers. Their recommendation was simple and blunt. It'd never do it. Instead, they proposed spreading the correction over many hours, smearing the adjustment so gradually that no system would ever experience a sudden jump. The problem is that smearing creates its own kind of trouble. Different organizations smear differently. Google has one method, Amazon has another, Microsoft has a third. During the hours when the smear is being applied, these systems would be running in slightly different versions of time. A timestamp from Google's servers would not mean exactly the same thing as a timestamp from Amazon's servers. For most purposes, the difference would be invisible. For systems that compare timestamps across platforms to verify transactions or synchronize data, the difference could matter enormously. In 2022, an international standards body took a dramatic step. They voted to eliminate the leap second entirely by 2035. No more adding, no more subtracting. Atomic time and Earth time would simply be allowed to drift apart without correction, and the growing gap would be dealt with through a different mechanism at some unspecified future point. The decision sounded clean. It sounded like a solution, but look closely and you see that it does not solve the underlying problem. It postpones it. The gap between the two versions of time will still grow. If the planet keeps accelerating, it will grow faster than anyone currently projects. And at some point, the accumulated difference will become too large to ignore, and the reckoning that was delayed will arrive with compound interest. Here is something strange that sits at the edge of this conversation. A small number of theorists have pointed out that the very concept of a unified global time may be an illusion we have imposed on a universe that does not naturally provide one. And Einstein showed that time runs at different speeds depending on gravity and velocity. A clock on a mountaintop ticks faster than a clock in a valley. A clock on a speeding airplane ticks slower than a clock on the ground. We paper over these differences with coordinated universal time, a single agreed-upon standard that pretends every point on Earth experiences the same moment simultaneously. But the pretense requires constant maintenance. Leap seconds were one form of that maintenance. Smearing is another. The elimination of leap seconds is yet another. Each fix is an attempt to hold together an agreement that the universe never actually signed. The debate over what comes after the leap second is genuinely unresolved. Some researchers advocate for a completely new timekeeping architecture, so one that acknowledges the planet's unpredictable rotation from the start, rather than treating it as an inconvenience to be patched Others argue that the current system, with modifications, is good enough for the foreseeable future. Still, others worry that the transition period itself, the years between the old system and whatever replaces it, will be the most dangerous window of all. A period when different organizations use different standards, different corrections, and different definitions of what time it actually is. What everyone agrees on is this: the systems that keep the modern world running were designed around a planet that behaved in a certain way. That planet is no longer behaving that way. And the systems most vulnerable to the mismatch are not abstract. They are the ones guiding aircraft through clouds, matching buyers to sellers in financial markets, synchronizing power across continental grids, and timing the delivery of radiation to a cancer patient's tumor. These are the systems that sing together in the great choir of modern infrastructure. And what happens when that choir loses its shared rhythm, when the sheet music itself becomes uncertain, is a story that touches every person alive. The notes are already drifting. The harmony is under strain. And the question is not whether the music will change, but whether we can learn the new melody fast enough to keep singing together. Every time you open a map on your phone and watch that small blue dot settle onto the street where you are standing, something extraordinary is happening in the sky above you. 20,000 kilometers overhead, a constellation of satellites is broadcasting signals timed to the nanosecond. Your phone catches those signals from at least 4 satellites at once, measures the tiny differences in when each one arrives, and uses those differences to calculate your position on the surface of a spinning planet. The whole system depends on one quiet assumption: that the satellites know exactly where the surface is, not roughly, not approximately, to within centimeters. And that knowledge comes from knowing precisely how fast the Earth is turning and where every point on its surface will be at any given microsecond. When the planet rotates faster than expected, the surface moves slightly ahead of where the satellites predict it should be. The error is small. For someone walking to a coffee shop, it is meaningless. The blue dot on your screen might drift by a few centimeters and you would never notice. But the global positioning system does not only guide people to coffee shops. Cargo ships navigate narrow straits at night using satellite positioning. A few meters of error in a channel barely wider than the ship itself is the difference between a clean passage and a hull-scraping rock. Precision-guided aerial systems depend on positioning accurate to centimeters. Survey teams building tunnels from both ends of a mountain rely on satellite data to ensure the two bores meet in the middle. For these applications, even a small drift in the model of Earth's rotation translates directly into a drift in the real world, and the consequences are not abstract. Ground control stations correct for variations in Earth's rotation constantly. This is not new. The problem has always existed, and the engineers who maintain these systems are skilled and experienced. But the corrections are applied in updates, not continuously. Between updates, the system operates on its last known model of how the planet is behaving. When the acceleration was small and predictable, the gaps between updates were easily covered by built-in safety margins. As the acceleration has grown more pronounced and less predictable, those margins are being consumed faster than they were designed for. There is another layer that most people never consider. The global positioning system is not alone in the sky. Russia operates its own constellation called GLONASS. The European Union operates Galileo. China operates Beidou. And each of these systems uses its own atomic clocks and its own ground correction stations. They are all coordinated to the same underlying time standard, but they do not update simultaneously. Their correction models do not always agree. When Earth behaves predictably, the disagreements between constellations are negligible. Position fixes from different systems produce essentially the same result. When Earth accelerates in ways that push against the correction models, the disagreements widen, and the devices that blend signals from multiple constellations to improve accuracy, which is exactly what modern aviation systems do, can begin receiving position data that contradicts itself. Modern instrument approach procedures at airports use satellite positioning to guide aircraft to within feet of a runway in conditions where the pilot cannot see the ground until the plane is roughly 30 meters above it. The tolerances are extraordinarily tight. The safety margins are real, but they are not unlimited. Aviation safety authorities have already issued technical bulletins acknowledging that increasing anomalies in Earth's rotational behavior require more frequent updates to navigation databases. The standard update cycle for aviation navigation data has historically been 28 days. Some categories of data are now being flagged for faster review. The sky is not falling, the planes are safe, but the engineers keeping them safe are working harder than they were a decade ago. Now, bring your attention from the sky to the ground beneath your feet and think about the electricity flowing through the walls around you. Power grids operate on alternating current at a fixed frequency, 50 cycles per second in most of the world, 60 cycles per second in North America. Grid operators synchronize these frequencies across interconnected systems spanning thousands of kilometers using coordinated universal time. When two sections of a grid are perfectly synchronized, electricity flows between them smoothly and efficiently. When they drift even slightly out of phase, the transfer becomes uneven. Energy pushes against energy instead of flowing with it. If the phase mismatch grows beyond certain limits, automatic protective systems disconnect the sections to prevent equipment damage. Those protective systems are calibrated to thresholds established by decades of operating experience under conditions where timekeeping was stable. Unusual timekeeping conditions, even subtle ones, can produce phase behaviors that fall outside the calibrated range. Grid operators in both Europe and North America have published technical analyses of how timekeeping anomalies affect grid behavior. Their conclusion was measured but clear. Current protective systems are adequate for the current level of anomaly. If the anomaly grows significantly, recalibration will be necessary. Financial markets add another dimension to this vulnerability. Stock exchanges in New York, London, Tokyo, and Frankfurt execute millions of trades per second. Each transaction carries a timestamp accurate to the microsecond. Those timestamps are synchronized to coordinated universal time, which is anchored to atomic clocks. In high-frequency trading, the sequence of orders matters as much as the orders themselves. A trade placed 1 microsecond before another trade takes priority. Regulatory bodies in some jurisdictions require financial institutions to maintain timestamp accuracy to the microsecond for legal compliance. When the planet's rotation creates a gap between atomic time and Earth time, the timestamps that govern the global financial system become ambiguous. A microsecond of ambiguity might sound like nothing. In high-frequency trading, a microsecond can represent millions of dollars of exposure. A full second of discontinuity, the kind a negative leap second would produce, does not just create confusion. It creates legal liability. Here is something that sits quietly in the background of all these discussions, rarely mentioned in public but well understood by the engineers who maintain hospital systems. Modern hospitals run on time-critical infrastructure more than most people realize. Medication dispensing systems log timestamps on every dose administered. Anesthesia delivery systems and patient monitors record continuous data against synchronized timestamps that form the legal medical record. Linear accelerators used in cancer treatment coordinate beam delivery with the rhythm of a patient's breathing. timed to fractions of a second. A 1-second discontinuity in any of these systems does not merely produce a data error. It creates a gap in the medical record that triggers automatic safety alerts and, in some cases, forces the equipment to shut down until a human being manually verifies that everything is still correct. Hospital IT teams have been aware of the leap-second problem since the 2012 incident that crashed systems worldwide. Most have implemented workarounds, but a workaround is not a solution. It is a bandage stretched over a wound that is slowly widening. There is a speculative but fascinating question that some engineers have begun asking privately. What happens when the rate of change in Earth's rotation exceeds the rate at which human institutions can update their correction systems? Not in a catastrophic, sudden way, but gradually, steadily. Each year the corrections come a little late. Each year the margins shrink a little more. Each year the systems built for a stable planet absorb a little more strain. The question is not whether any single system will break. Most are robust enough to handle considerable pressure. The question is what happens to the connections between systems. The places where aviation timing meets financial timing, meets power grid timing, meets hospital timing. Each one might hold individually, but the joints between them, the places where one system's output becomes another system's input, those are where strain accumulates most dangerously. And all of this, every satellite, every power grid, every trading floor, every hospital monitor, depends on understanding why the planet changed speed in the first place. The surface systems can only compensate for what they can predict. And prediction requires understanding the cause. The atmosphere contributes, the oceans contribute, the ice contributes. But the deepest and most powerful force shaping Earth's rotation does not come from any of these. It comes from a place no human has ever visited. A place where iron flows like a dark river under pressures that would crush diamonds to dust. A place 2,000 miles straight down, where the real engine of this planet turns in silence and absolute darkness. If you could somehow drill straight down from the place where you are sitting right now, through the thin crust of rock beneath your feet, through the upper mantle where stone behaves more like slow-moving clay, through the lower mantle where pressure squeezes minerals into crystal structures that do not exist anywhere on the surface. And if you kept going past the point where the temperature rises beyond anything your mind can comfortably picture, you would eventually reach a boundary, roughly 1,800 miles down. Below that boundary, everything changes. The rock ends. The solid gives way to liquid. And you enter a world that is among the strangest places in the known universe. Not because it is far away, but because it is directly beneath you, closer than the moon, closer than any satellite, and yet more alien than the surface of most planets we have photographed. This is the outer core, just a shell of liquid metal roughly 1,400 miles thick, composed mostly of iron and nickel, heated to temperatures that exceed the surface of the sun. At those temperatures, iron should glow. It should radiate light so intense that nothing could look at it directly. But there is no light here. The darkness is absolute. No photon has reached this depth since the planet formed. The iron does not glow because the pressure, more than 1,000,000 times the atmospheric pressure at the surface, changes the rules. Energy moves differently here. Heat transfers through convection, through the physical movement of the liquid metal itself, rising and falling in massive currents that sweep through the darkness like slow rivers of molten iron flowing through an ocean that has no surface and no shore. These currents are not gentle. They are not small. They move at speeds of tens of kilometers per year, which sounds slow until you remember that this is a fluid denser than lead, flowing under pressures that would crush any material humans have ever manufactured. The energy involved is extraordinary, and the currents carry something with them that changes everything about the planet above. They carry electrical charge. Moving liquid iron is a conductor, and a moving conductor generates a magnetic field. This is not a metaphor. It is basic physics, the same principle that makes an electric generator work. Spin a coil of copper wire inside a magnetic field, and you produce electricity. The outer core works the same way, but on a planetary scale. The flowing iron creates electrical currents. The electrical currents create magnetism, and the magnetism feeds back into the flow, organizing the currents into patterns that sustain the field over billions of years. Scientists call this process the geodynamo. It is the engine that produces the magnetic field wrapping the entire planet in an invisible shield that extends thousands of miles into space. That shield is not a luxury. It is the reason you are alive. Streaming outward from the sun at roughly 1,000,000 miles per hour is a constant wind of charged particles, protons, and electrons moving with enough energy to strip away an atmosphere molecule by molecule. Mars once had a thick atmosphere. It lost its magnetic field billions of years ago, and the solar wind slowly peeled its air away, leaving a cold, barren surface exposed to radiation. Earth avoided that fate because the geodynamo kept running. The liquid iron kept flowing. The magnetic field kept deflecting the solar wind around the planet like water flowing around a stone in a river. Every breath you take exists because iron is moving in the dark 2,000 miles below you. But the outer core does something else, something that connects directly to the mystery of Earth's acceleration. It physically interacts with the rotation of everything above it. The outer core does not rotate at exactly the same speed as the mantle and crust sitting on top of it. There is a coupling between them, transmitted through pressure and electromagnetic forces, but the coupling is imperfect. The core has some rotational independence. It can speed up or slow down relative to the layers above, and when it does, the effect does not stay buried. It propagates upward. When the massive currents of liquid iron shift their flow patterns, when columns of rising and sinking metal reorganize themselves in response to changing temperature gradients or shifts in the inner core below, they exert torque on the mantle above them. Torque is a rotational force. It is the push you feel when you try to hold a spinning wheel and it resists changing direction. When the outer core pushes rotationally against the mantle responds. The crust, riding on top of the mantle, responds with it, and the rotation rate of the surface changes. This is not theory. Researchers studying the correlation between changes in Earth's magnetic field and changes in its rotation rate have found a pattern. When the magnetic field fluctuates in certain ways, the rotation tends to change in specific, predictable directions. The connection is not perfectly understood. The mechanisms are still being debated, but the correlation is strong enough that geophysicists now treat core dynamics as one of the primary drivers of decade-scale rotation variations. The acceleration that became measurable at the surface around 2016 coincides with changes in the outer core's circulation patterns detected by satellite magnetic field measurements. The European Space Agency's SWARM mission, a constellation of 3 satellites mapping Earth's magnetic field with extraordinary precision, has captured these changes in real time. The timing between the magnetic signal and the rotation signal is not a coincidence. Here is where the story reaches into truly strange territory. There is a hypothesis, not yet proven but physically grounded, that the outer core may have 2 stable flow states, much like a switch that can sit in one of 2 positions. If the current flow pattern represents one state, a transition to the other could produce rapid changes in both the magnetic field and the rotational coupling to the surface. Such a transition would not happen overnight. It would unfold over decades, but during the transition, the effects on the surface could be unpredictable, producing accelerations and decelerations that existing models are not equipped to forecast. Whether we are in such a transition is genuinely unknown. What the data shows clearly is that the outer core is not behaving the way it was behaving 30 years ago. The magnetic field is changing, the flow patterns are shifting, and the rotational effects of those shifts are arriving at the surface in the form of an acceleration that the models did not predict. The iron ocean beneath your feet is restless. Its currents are reorganizing, and the consequences of that reorganization do not stop at the boundary between the core and the mantle. They travel further. They reach deeper, because the outer core is not the innermost layer of this planet. It wraps around something even more extraordinary, a solid sphere sitting at the very center of the world, surrounded on all sides by liquid iron, rotating on its own terms, answering to its own forces. A ball of crystallized iron roughly the size of the moon, turning slowly in the deepest darkness imaginable. And in recent years, scientists discovered that this innermost heart of the planet had done something that no one expected. It changed direction. The story of that reversal, and what it means for everything above, begins at the very center of the Earth, at the very center of everything, past the liquid iron ocean we just traveled through, past the storms of molten metal and the invisible rivers of electrical charge. There is something solid, a sphere of iron and nickel roughly the size of the moon, sitting at the heart of the planet in conditions that should make its existence impossible. The temperature here is roughly 9,000 degrees Fahrenheit. That is comparable to the outer surface of the Sun. At that temperature, an iron should be liquid. Everything should be liquid. Nothing should hold its shape in heat that intense. And yet, this iron is solid. It holds together not because the heat is not real, but because something even more powerful is fighting against it. Pressure. The weight of the entire planet, every layer of rock, every ocean, every mountain, every molecule of atmosphere presses inward from all directions. The pressure at Earth's center is more than 3 million times the pressure at the surface. Under that kind of force, atoms are squeezed so tightly together that even temperatures hot enough to melt the surface of a star cannot shake them apart. The iron locks into a crystalline structure, so dense, so rigid, that it remains solid inside a furnace that would vaporize anything you have ever touched. This is the inner core. It floats inside the liquid outer core the way a ball, bearing, floats in thick oil. There is no rigid connection between the inner core and the mantle above. No shaft, no rod, no solid bridge linking the center to the surface. The only medium through which forces pass between them is the liquid iron of the outer core. Pressure waves, electromagnetic forces, and gravitational interactions travel through that liquid layer and provide the only communication between the deepest sphere and the world you live in. And because there is no rigid link, the inner core can rotate independently. It does not have to spin at the same speed as the mantle or the crust. It can turn faster. It can turn slower. It can, in principle, go its own way entirely. For decades, geophysicists suspected it did exactly that. The evidence came from an unexpected source: earthquakes. When a powerful earthquake strikes anywhere on Earth, it sends seismic waves radiating outward in every direction, including straight down through the core and out the other side. Scientists at seismograph stations around the world record those waves and use their travel times to build a picture of the planet's interior, much the way a doctor uses ultrasound to see inside the body. Different materials transmit seismic waves at different speeds, and the inner core, with its iron crystal structure aligned in a particular direction, transmits waves slightly faster along some paths than others. By comparing recordings of similar earthquakes over many years, researchers noticed something. The travel times were changing. Waves passing through the inner core were arriving at slightly different moments in recent decades than they had in earlier ones. The best explanation was that the inner core was rotating, slowly turning relative to the surface and changing the angle at which its crystal structure met the passing waves. Through the 1990s, the data was relatively clear. The inner core appeared to be rotating slightly faster than the mantle and crust above it. This was called superrotation. It was not dramatic, just a fraction of a degree per year, but it was consistent across multiple studies using different datasets from different parts of the world. The inner core was quietly outpacing the surface, spinning ahead of us by a tiny amount each year. Then something changed. A study published in 2023 in the journal Nature Geoscience examined a longer stretch of earthquake data and reached a conclusion that sent a ripple through the geophysics community. The superrotation had slowed. Sometime around 2009, the inner core appeared to have decelerated until it matched the rotation of the mantle above it. Then it slowed further. By approximately 2010 to 2012, it seemed to be rotating slightly slower than the surface. The researchers concluded that the inner core had reversed its rotation relative to everything above it. Take a moment to sit with that. The solid iron heart of the planet you are standing on, a sphere as wide as the moon, buried 3,600 miles beneath your feet, appears to have slowed, stopped, and begun turning in the opposite direction from the world surrounding it. The forces involved are immense. The angular momentum of the inner core is not trivial. It is a massive object spinning inside a fluid medium, and any change in its rotation does not stay contained. It propagates outward through the liquid iron of the outer core, through the mantle, through the crust, altering the rotational dynamics of every layer it touches. The connection to the surface acceleration follows a principle as fundamental as anything in physics: conservation of angular momentum. When the inner core decelerates, that rotational energy does not vanish. It transfers upward. It passes through the electromagnetic and gravitational coupling of the outer core to the mantle, and from the mantle to the crust. The surface receives the angular momentum the inner core gives up. The result is a subtle but measurable increase in the rotation speed of everything above. Think of it like two figure skaters holding hands and spinning together. If one skater suddenly slows down, the other speeds up. The total momentum stays the same, but it redistributes between them. The inner core slowed, the surface sped up, and the timing fits. The inner core's apparent deceleration in the late 2000s aligns, with an appropriate delay for the transfer to propagate upward through the layers, with the surface acceleration that became measurable starting around 2016. Not everyone agrees with this interpretation. The study has credible critics who point to alternative explanations. The inner core's surface is not smooth. It has ridges and valleys of iron crystal that could scatter seismic waves differently over time without requiring any change in rotation. Changes in the outer core above could also affect wave travel times. The debate is active and genuine, but what both sides agree on is that something changed. The inner core's seismic signature in the 21st century is different from its signature in the 20th. Whether that difference reflects a full rotational reversal or a subtler structural change, the deep interior of the planet is not doing what it was doing a generation ago. Here is a thought that lives at the speculative edge of this science. Some researchers have proposed that the inner core undergoes regular oscillations, swinging between phases of faster and slower rotation on cycles of roughly 60 to 70 years. If that pattern holds, the current reversal is not a one-time event. It is part of a deep planetary rhythm that has been beating beneath us for as long as the inner core has existed. A rhythm too slow for any single human lifetime to witness completely, but long enough to leave its signature in the rotation data if you look across the full span of modern measurement. What is certain is this: the deepest part of Earth has shifted its behavior. Angular momentum is moving upward through the layers, and the surface is responding. But the core is not the only force reshaping how this planet spins. Far above, at the top of the world and the bottom, something else is happening. Something visible from space. The ancient ice that has sat on the poles for thousands of years is breaking apart at a pace that has surprised even the scientists who study it most closely. And as it disappears, it is physically changing the shape of the spinning world beneath it. In every physics classroom, there is a demonstration that never fails to amaze. A person sits on a spinning stool, arms stretched wide, holding a heavy weight in each hand. The stool turns slowly. Then the person pulls their arms inward, bringing the weights close to their body. Instantly, without anyone pushing, without any motor or engine, the stool spins dramatically faster. The reason is one of the most fundamental laws in physics: conservation of angular momentum. When you move mass closer to the axis of rotation, the spinning speed increases to compensate. When you move mass away from the axis, the spinning slows down. No energy is added or removed. The speed changes purely because the distribution of weight has changed. Earth works by exactly the same principle. And right now, the distribution of weight on this planet is changing in ways that can be measured from space. For most of the last 20,000 years, enormous ice sheets covered large portions of Earth's surface, concentrated heavily near the poles. The North American ice sheet alone was more than 3 kilometers thick in places, a mountain of frozen water pressing down on the land beneath it. These polar ice masses sat close to Earth's rotation axis, the imaginary line running from the North Pole through the center of the planet to the South Pole. Mass near the axis behaves like the person on the stool with arms pulled in. It allows the planet to spin at a certain speed. When that mass moves away from the axis toward the equator, the planet should slow down, just like the person on the stool extending their arms. For thousands of years following the last ice age, the slow melting of ancient glaciers did exactly that. Water that had been locked in polar ice flowed into the oceans and spread toward lower latitudes. The planet's moment of inertia, the rotational equivalent of how its weight is distributed, shifted outward. The spin slowed a tiny bit. This contributed to the long-term deceleration that was already being driven by the moon's tidal pull. Everything moved in the same direction. Everything was consistent. But what is happening now is different from the slow, steady melt of the post-glacial period. It is faster, much faster. The Greenland ice sheet is currently losing roughly 280 billion metric tons of ice per year. Antarctica is losing approximately 150 billion metric tons per year. These numbers are large enough to detect from orbit, and they are not stable. They are accelerating. The rate of ice loss today is significantly higher than it was in the 1990s, and the rate in the 1990s was higher than in the decades before that. But models published in the early 2000s predicted ice loss at levels that the real world surpassed well ahead of schedule. The planet is shedding its polar ice faster than scientists expected. The measurement comes from a remarkable pair of satellites called GRACE, the Gravity Recovery and Climate Experiment, and its successor, GRACE follow-on. These satellites fly in formation roughly 350 miles above the surface, separated by about 200 kilometers. They constantly measure the distance between each other with extraordinary precision, down to a fraction of a micrometer. When mass shifts on the planet's surface, the gravitational field shifts with it. One satellite feels the tug of the changed gravity a moment before the other, and the distance between them changes by an almost impossibly small amount. From those tiny variations, scientists have mapped the redistribution of mass across the entire planet in real time. The picture is striking. The poles are losing mass. The mid-latitude ocean basins are gaining it. Water that was frozen at the top and bottom of the world is spreading outward toward the middle. By the physics of the spinning stool, this should be slowing the planet down, and in the long run, it will. But the short-term picture is more complicated. The redistribution is not uniform. Different parts of the ice sheets melt at different rates. Different ocean basins receive water at different depths and latitudes. The interaction between where the mass is going and the three-dimensional shape of the spinning planet creates effects that are not simply the sum of their parts. One of those effects is something most people have never heard of. The planet's rotation axis, the actual line around which everything spins, is physically moving, not the magnetic pole, which wanders for its own reasons. The geographic pole, the true spin axis of the Earth. For most of the 20th century, the North Pole drifted slowly toward northern Canada at a rate of a few centimeters per year, pushed by the continuing rebound of land that had been compressed under Ice Age glaciers. Then, around the year 2000, the direction changed. The pole turned eastward toward Greenland, and the speed of the drift increased substantially, from a few centimeters per year to roughly 17 centimeters per year over the course of the 2000s and 2010s. When researchers analyzed the cause using the GRACE satellite data, the answer was clear. The primary driver was ice loss from Greenland. Greenland sits in a specific position relative to the rotation axis. As its ice sheet loses mass, the distribution of planetary weight changes in a way that pulls the pole in a new direction. A West Antarctic ice loss contributes as well, pulling in a slightly different direction and adding to the net eastward trend. The geographic North Pole, the point on the surface directly above the rotation axis, is now measurably different from where it was when you were born. This is confirmed by satellite measurements. It is not a model prediction. It is an observation. And while the shift is not large enough to change where you see the North Star in the sky during your lifetime, it matters enormously to the systems that depend on knowing exactly where the rotation axis is. Every satellite navigation system, every geodetic survey, every timing network uses the precise location of the rotation axis in its calculations. The International Earth Rotation and Reference System Service publishes updated Earth orientation parameters regularly, and those parameters feed directly into the correction models for GPS, Galileo, GLONASS, and Beidou. The updates have been coming more frequently in recent years because the axis is moving faster. There is a haunting detail about melting ice that most people find surprising when they first encounter it. Sea level does not rise evenly. The intuition says water fills a bowl uniformly, but the ocean is not a simple bowl. A massive ice sheet has its own gravitational pull. It is so heavy that it attracts ocean water toward it, piling the sea slightly higher near the ice. When the ice melts and that gravitational attraction weakens, the water near the poles actually drops. It flows away toward the tropics and the southern hemisphere, where sea levels rise disproportionately. Coastlines near Greenland may see sea levels fall slightly even as Greenland melts. Coastlines in the Pacific Islands, in Southeast Asia, in the tropical Atlantic, sea levels rise far more than the global average would suggest. Some researchers have raised an unsettling possibility at the edges of this science. If ice loss crosses certain thresholds, it could trigger drainage reorganizations within the ice sheets themselves. Changes in the slope of the ice surface caused by uneven melting could redirect meltwater rivers beneath the ice, lubricating the base and accelerating the flow of glaciers into the sea. This kind of feedback, as where ice loss causes further ice loss, independent of whatever started the melting in the first place, is called a tipping point. And the uncomfortable truth is that tipping points are, by definition, very difficult to detect before you have already crossed them. The weight of the world is shifting. The axis is drifting. The ice is breaking apart faster than we predicted. And when the weight of a spinning object changes, it does not only affect speed, it affects something else, something rhythmic, something that has been one of the most reliable heartbeats of this planet for as long as we have measured it. A slow, steady wobble traced by the pole as Earth rocks gently on its axis every 14 months. A wobble that, in the early years of this century, did something deeply strange. It nearly stopped. Earth does not spin like a perfectly balanced wheel. It wobbles. It has always wobbled. If you could hover above the North Pole and watch the planet turn beneath you with instruments sensitive enough to track the movement, you would see the pole itself tracing a small, slow circle on the surface. Not a fixed point, a wandering one, drifting in a pattern that repeats roughly every 14 months, in drawing an irregular loop about 9 meters across at the pole before starting over again. This is the Chandler Wobble, named after Seth Carlo Chandler, the American astronomer who documented it in the 1890s. And for more than a century, it has been one of the most dependable rhythms in all of geophysics. The cause is geometry. Earth is not a perfect sphere. It is slightly flattened at the poles and slightly bulging at the equator, squeezed outward by the centrifugal force of its own rotation. A perfectly spherical, spinning object would rotate smoothly around its axis without any wobble at all. But a slightly squashed spinning object does not behave so cleanly. Its rotation axis and its geometric axis do not perfectly align. The result is a gentle rocking motion, a wobble that is built into the physics of the planet's shape. It is as natural as the way a slightly lopsided top traces circles on a table as it spins. For a perfectly rigid body, this wobble should eventually die out. Friction and internal resistance would slowly drain its energy, and the axis would settle into perfect alignment. But Earth is not perfectly rigid. The crust flexes under tidal forces. The mantle flows slowly over geological time. The oceans slosh back and forth with tides and currents and storms. These movements continuously feed energy back into the wobble, re-exciting it, keeping it alive even as dissipation works to quiet it down. The balance between the energy being put in and the energy being lost has kept the Chandler wobble going at a more or less steady amplitude for as long as anyone has measured it, until it nearly stopped. Around the year 2000, something changed. The amplitude of the Chandler wobble, how large the circle traced by the wandering pole was, it began to shrink. By around 2005 to 2006, it had dropped to roughly 1/5 of its typical size. The wobble that had been beating like a quiet drum for more than a century had faded to almost nothing. The pole was barely moving. The rhythm that geophysicists had come to treat as one of the most reliable constants in Earth's rotational behavior had nearly gone silent. This was noticed immediately. Papers were published. Conferences debated the cause. The leading hypothesis pointed to the oceans. Specifically, to changes in deep ocean circulation that had shifted where cold, dense water sinks to the ocean floor. The pattern of pressure on the ocean bottom had changed in a way that damped the forces that normally keep the wobble going. Ocean temperature changes associated with a prolonged La Niña cycle were identified as a likely contributor. The excitation that had sustained the wobble for over a century was being absorbed by a reorganized ocean, and without that excitation, the wobble faded. Think of it this way. Imagine a child on a swing. The swing naturally wants to slow down. Friction at the hinge, air resistance, the rope stretching slightly with each pass, all work to drain the energy of the motion. But someone stands behind the child and gives a small push at exactly the right moment in each cycle. Those pushes do not need to be large. They just need to be timed correctly to match the natural frequency of the swing. The swing keeps going. Now imagine the person giving the pushes steps away. Not dramatically. They do not leave. They simply start pushing at the wrong moment, slightly out of sync with the swing's natural rhythm. The pushes still happen, but they no longer add energy efficiently. Some pushes might even work against the swing, slowing it slightly. The amplitude drops. The swing arcs grow shorter. If the mistiming continues long enough, the swing nearly stops. That is roughly what happened to the Chandler wobble. The ocean did not stop interacting with the rotation. It changed how it interacted. The timing of the pressure variations on the ocean floor shifted out of alignment with the wobble's natural 14-month period. The energy that should have sustained the wobble was no longer arriving at the right moment. And without that correctly timed input, the wobble faded towards silence. The wobble eventually recovered. By the late 2000s, it was operating closer to its normal amplitude again, though researchers continued to watch it carefully. But the episode revealed something that made the scientific community deeply uncomfortable. A force as fundamental as the Chandler wobble, yet operating for as long as Earth has had its current shape, had been significantly suppressed by changes in ocean circulation. The ocean had not done anything dramatic. It had not boiled or frozen or disappeared. It had simply reorganized its deep currents enough to change the timing of its interaction with the planet's rotation. And that had been sufficient to nearly silence a planetary rhythm that had been beating for millions of years. The implications were wider than the wobble itself. If ocean changes could suppress something as fundamental as the Chandler wobble, what else could they affect? What other rotational features, what other rhythms and patterns in the way the planet turns, were vulnerable to shifts in the deep ocean circulation? And if the ice redistribution we traced in the last passage continues at its current rate, if more and more frozen water enters the ocean at higher and higher speeds, how will the ocean's changing mass and temperature and circulation interact with the other wobbles, the other rhythms, the other delicate balances that keep the spinning Earth behaving in ways our infrastructure was designed to expect? Here is where a speculative thread enters the weave. A small number of researchers have proposed that the Chandler wobble may not be purely mechanically driven. They suggest that electromagnetic coupling between the liquid outer core and the lower mantle might contribute to its excitation in ways that are not yet captured in standard models. If this is true, then the wobble's near disappearance might not be entirely an ocean story. It might also carry a faint signal from the same core dynamics that are driving the surface acceleration and the magnetic field changes described earlier in this journey. The idea remains unproven, but it connects the deepest layers of the planet to its surface behavior through yet another pathway, adding another thread to an already complex tapestry. What is firmly established is that the planet's rotational behavior is not governed by any single force. It is the product of interactions between layers, between the solid inner core and the liquid outer core. between the mantle and the crust, between the oceans and the atmosphere. Each layer talks to the others through pressure, gravity, friction, and electromagnetic forces. When one layer changes its behavior, the message propagates through the system, arriving at different layers at different times with different strengths. The result is a rotation that is always fluctuating, always adjusting, always responding to a conversation happening across thousands of miles of depth. And one of the loudest voices in that conversation, right now, is not coming from below. It is coming from above, from the magnetic shield that wraps the planet in its protective embrace. A shield that is thinning, a shield that has developed a wound over an entire ocean, a wound that is growing, deepening, and showing the first signs of splitting in two. The story of that wound and what it reveals about the forces reshaping this planet from the inside out. What lies directly ahead. Picture the planet wrapped in an invisible shield, not a physical wall, not something you could touch or see or feel standing on the surface, but something real, something measurable, something that has been protecting every living thing on Earth for billions of years. The magnetic field extends thousands of miles into space in every direction, deflecting the constant stream of charged particles flowing outward from the sun. Without it, those particles would gradually strip away the atmosphere the way sandpaper strips away wood, slowly, relentlessly, until nothing breathable remained. The magnetic field is not decorative, it is foundational. It is the reason this planet is alive. But the shield is not uniform. It does not wrap the planet evenly like a perfect shell. It is generated by the turbulent asymmetric flow of liquid iron in the outer core, and the result is a field with regional variations, stronger in some places, weaker in others, shifting in strength and location over decades and centuries as the iron currents beneath rearrange themselves. Most of those regional variations are relatively minor, background fluctuations in a system that overall holds together. But one region stands apart. One region has been drawing the attention of researchers with increasing urgency for decades, and that region sits directly over the South Atlantic Ocean, stretching across much of South America, growing larger and deeper with every passing year. It is called the South Atlantic Anomaly, and it is the largest known weakness in Earth's magnetic shield. In the heart of the anomaly, the magnetic field is roughly 40% weaker than it would be at equivalent latitudes elsewhere on the planet. 40%. Not a subtle variation. Not something at the edge of detection. A gap in the shield so pronounced that it has measurable consequences at altitudes where satellites orbit. Earth's magnetic field normally deflects charged particles from the Sun high enough that satellites in low Earth orbit pass beneath the danger zone, protected by the field above them. In the South Atlantic Anomaly, the field is so weak at lower altitudes that charged particles penetrate much further before being deflected. Satellites passing through this region encounter elevated radiation levels that can cause electronic malfunctions, corrupted data, and hardware damage. The International Space Station crosses through the anomaly on many of its orbits. Astronauts are warned when the station is passing through. Sensitive instruments are powered down or protected. Extra precautions are taken. This is standard operating procedure, not because the anomaly is new, but because it has been documented since the 1950s, and every mission that passes through it must account for the elevated radiation environment. The hardware that controls life support, navigation, and communication on a crewed spacecraft cannot afford unexpected disruptions from cosmic particles punching through a weakened shield. What is new is not the anomaly's existence. What is new is its behavior. Over the past several decades, the anomaly has been expanding in area and deepening in intensity. The region of weakened field is getting larger. The minimum field strength within it is getting smaller. And satellite magnetic field measurements from the European Space Agency's SWARM mission have revealed something more troubling still. The anomaly appears to be developing a second minimum, a split. Where there was once one central weak spot, the data now shows signs of two separate regions of minimum intensity beginning to emerge, as if the original wound in the shield is tearing along a seam. The cause of the anomaly is tied directly to what is happening in the outer core beneath that region of the planet. Under the South Atlantic, there is an unusual structure in the outer core called a low-velocity zone. In this zone, the liquid iron moves differently from the surrounding material. The flow is disrupted. The currents that normally sustain the magnetic field in that region are behaving in an anomalous way. Some researchers believe this zone represents a patch of reversed magnetic polarity deep within the outer core, a region where the local field alignment is opposite to the global dominant direction. The interaction between this reversed patch and the overall field above it produces the surface weakness. Where the two opposing field directions meet and partially cancel each other out, the shield thins. The reversed patch is not static, it is growing. Its boundaries have expanded over the decades that researchers have been tracking it. And this connects back to the rotation story in a way that is important and often overlooked. Changes in outer core flow patterns affect the magnetic field. Yes, changes in the magnetic field affect the electromagnetic coupling between the outer core and the mantle sitting above it. Changes in that coupling affect the transfer of angular momentum between the core and the surface. The South Atlantic anomaly is not just a radiation hazard for satellites and astronauts. It is a visible symptom of changes happening in the outer core. The same outer core whose shifting circulation patterns appear to be connected to the surface acceleration. The two phenomena share an origin. They are different expressions of the same restlessness in the liquid iron world below. Now, consider the longer view. The current rate of global magnetic field weakening, measured since systematic observations began in the early 19th century, is roughly 9% over approximately 180 years. That is a significant rate of change by historical standards. Whether it represents the beginning of a full magnetic reversal, a temporary excursion that will correct itself, or something in between is genuinely unknown. But the question is not hypothetical. Magnetic field reversals are one of the confirmed realities of Earth's deep history. The planet's north and south magnetic poles have flipped hundreds of times. The average gap between reversals is roughly 200 to 300,000 years. The last full reversal, called the Brunhes-Matuyama reversal, occurred approximately 780,000 years ago. By average statistics alone, we are well past due. That phrase requires careful handling. The timing of reversals is not clockwork. The gap between reversals ranges from tens of thousands to tens of millions of years. Being past the average interval tells us very little about when the next reversal might occur. What it tells us is that reversal is normal. It has happened hundreds of times. Life survived every one. But survived requires some unpacking. During a reversal, the field does not flip instantaneously. The transition takes thousands of years. During that transition, the field weakens significantly, potentially dropping to 10 or 20% of its normal global strength. The protection against charged particles from the sun is reduced across most of the planet. Satellites malfunction more frequently. Power grids are more vulnerable to solar storm damage. Animal species that navigate using magnetic sensing, migratory birds, sea turtles, certain fish, lose their compass. Radiation reaching the surface increases enough to affect biological systems in measurable ways. Here is something at the speculative edge of this discussion that researchers have raised carefully. The Lachamp excursion, a period roughly 42,000 years ago when the magnetic field weakened dramatically and the poles briefly shifted before recovering without a full reversal, left signatures in ice cores, cave mineral deposits, and ancient tree rings. Some researchers have connected that period of weakened field to accelerated climate changes and shifts in megafauna populations in certain regions. The causal chain is debated, but the signatures are real. They suggest that when the shield thins significantly, the consequences extend beyond radiation counts on satellites. They reach into the biology and climate of the planet's surface. The current anomaly, the growing wound over the South Atlantic, the slow weakening of the global field, the expanding reversed polarity patch in the outer core, these are not independent data points. They are connected signals from the same system, and that system is not only shaping the magnetic shield above, it is coupled to the rotation below. The iron that generates the field also drives the spin. The currents that are reorganizing beneath the South Atlantic are part of the same global flow pattern that is altering the rotation of everything above. The shield and the spin are telling the same story. And the atmosphere surrounding both of them is not a passive witness. It is an active participant, carrying its own angular momentum, responding to ice loss, ocean warming, and magnetic changes, and pushing those responses back into the rotation in ways that are only now being fully understood. The atmosphere is not light. Most people think of air as something weightless, something that floats above the solid world without pushing on it. But the atmosphere has mass, enormous mass. The total weight of the air wrapping this planet is roughly 5.1 quintillion kilograms. That number is so large it barely registers as meaningful. To give it shape, consider that it is comparable to the mass of large mountain ranges. All the air above you, from the ground where you are resting to the edge of space, weighs as much as mountains, and that mass moves constantly. It shifts from one latitude to another as weather systems develop, grow, and dissolve. It pushes from hemisphere to hemisphere with the seasons. It accelerates in jet streams that circle the planet at hundreds of kilometers per hour. And every time it moves, it pushes against the rotating surface beneath it. This is not a theoretical coupling. It is measured directly and continuously. Meteorologists and geodesists have spent decades comparing atmospheric angular momentum data with Earth rotation data. The match is striking. When the atmosphere gains angular momentum, typically when large-scale wind systems strengthen and accelerate, the solid Earth beneath slows down slightly. When the atmosphere loses angular momentum, the solid Earth speeds up slightly. The total angular momentum of the Earth system, the combined momentum of the solid planet, the oceans, and the atmosphere must be conserved. When one part speeds up, another must slow down. The atmosphere and the planet are engaged in a continuous, silent exchange of rotational energy that never stops. The dominant signal in this exchange is seasonal. Winter in the northern hemisphere produces stronger, more intense jet streams. Those high-altitude rivers of air racing from west to east at the top of the troposphere carry substantial angular momentum. The solid Earth responds by slowing fractionally. In summer, when the jet streams weaken and the atmospheric mass redistributes, the solid Earth speeds up fractionally. The effect amounts to roughly 1 millisecond of variation in the length of a day across the year, small enough to ignore in daily life, large enough to measure precisely with modern atomic clocks and to account for in the correction models of satellite navigation systems. But the seasonal signal is not the whole story. There are non-seasonal components that are larger and less predictable. The most significant is El Niño. During a strong El Niño event, the trade winds that normally blow westward across the tropical Pacific weaken dramatically. Those trade winds carry angular momentum. When they weaken, the atmosphere releases angular momentum into the ocean, and through the ocean's interaction with the solid Earth, the planet's rotation rate changes detectably. Strong El Niño events in 1982 to 1983, 1997 to 1998, and 2015 to 2016 each produced measurable rotation anomalies. The planet sped up or slowed down by fractions of a millisecond in direct response to a change in tropical Pacific wind patterns. The 2015 to 2016 El Niño is particularly relevant to this story, as it was one of the strongest El Niño events ever recorded, and it coincides closely with the beginning of the surface acceleration trend that researchers have been tracking across the years since. This does not mean El Niño caused the acceleration. The speed-up has persisted long after the El Niño ended, and its magnitude is larger than El Niño alone can explain. But the 2015 to 2016 event may have contributed to the initial departure from baseline behavior, a push in the direction of acceleration that the deeper forces of the core and ice redistribution then sustained and amplified. Here is where the atmosphere becomes not just a contributor, but an integrator. The atmosphere receives signals from every other system on this planet and combines them into a single mechanical force applied to the rotating surface. Ice loss in Greenland and Antarctica changes the temperature contrast between the Arctic and the mid-latitudes. That temperature contrast drives the jet stream. A weakening contrast produces a slower, wavier jet stream that does not circle the poles as cleanly as it once did. Instead, it meanders in large loops, dipping far south and then sweeping far north, carrying cold polar air into temperate regions and pushing warm air toward the poles. This shift in jet stream behavior has been documented across the past 2 decades and is directly linked to Arctic warming driven by the loss of sea ice. A wavier jet stream redistributes atmospheric angular momentum differently across latitudes. Instead of carrying most of its momentum in a tight band around the mid-latitudes, it spreads it more broadly. The interaction between this redistributed momentum and the planet's surface changes the rotational forcing in ways that standard seasonal models do not fully capture. Some of that change adds to the acceleration, some subtracts from it. The net effect at any given moment depends on the exact shape of the jet stream at that time, which can change dramatically within weeks. The stratospheric polar vortex adds another layer to this. The polar vortex is a large area of low pressure and cold air that forms in the stratosphere above the poles during winter. It normally spins in a tight, stable circle containing the coldest air at high latitudes. When the vortex is strong, it stays organized and compact. When it weakens, it can split or become distorted, allowing cold stratospheric air to spill downward and equatorward. This phenomenon, sometimes called a sudden stratospheric warming, distributes atmospheric mass differently across latitudes and creates a brief but measurable rotational pulse in the solid Earth below. These sudden stratospheric warming events have become more frequent in recent decades, and each one produces a rotation signal that arrives at the surface within days of the stratospheric disruption, a reminder that the atmosphere and the solid planet are in close, continuous communication. Now turn from the atmosphere to the ocean below it, because the oceans carry their own angular momentum and are changing in ways that add to everything above. The Atlantic meridional overturning circulation is the deep ocean conveyor system that carries warm surface water northward along the eastern coast of the Americas and toward Europe, then cools, sinks as cold, dense water, and returns southward as a deep bottom current. It has been weakening. Multiple independent datasets confirm that this circulation is now at its weakest point in at least 1,000 years. Some studies suggest the weakening has accelerated in recent decades. The rotational implications of a weakened circulation are subtle but real. The circulation transports angular momentum through the ocean basins in a specific pattern. When that pattern changes, the distribution of ocean angular momentum changes. Some components of the change add fractionally to Earth's rotation speed, others subtract. The net effect depends on the details of how the circulation is reorganizing, and those details are still being worked out. What is clearer is the thermodynamic side of ocean change. Warmer ocean water expands, sea level rises not only because ice melts, but because the water itself occupies more volume as it warms. A warmer, expanding upper ocean changes where angular momentum resides within the water column. The boundary between warm surface water and cold deep water deepens. Mass redistributes vertically in ways that interact with the planet's rotation budget. And there is one more connection that sits at the edge of this picture. Warmer ocean surface temperatures drive more intense and more frequent tropical storms. A major hurricane is a rotating atmospheric structure that carries angular momentum. When it forms and decays, it redistributes rotational energy between the atmosphere and the ocean in ways that leave a small but detectable signal in the planet's rotation rate. An ocean generating more intense storms more frequently is an ocean that perturbs the rotation budget more often. The cumulative effect builds over years and decades, contributing to a rotational environment that is measurably more variable than it was a generation ago. All of these forces, the atmosphere, the ocean, the ice, the core, are combining right now in ways that are still being disentangled by researchers. But there is a record of what happens when Earth's systems move together like this. A record written not in digital data or satellite measurements, but in stone. In coral skeletons older than civilization. In sediment layers pressed flat by ancient tides. In lava that froze in place hundreds of millions of years ago and locked inside itself the direction and strength of the magnetic field at the exact moment it hardened. That record holds answers that no modern instrument can provide. And it is the oldest and most patient voice in this entire conversation. There is a kind of library buried inside the Earth. Not a room of books, not markings on clay or paper. Something far older than any human record. Layers of rock and coral and frozen lava hold physical memories of how this planet has behaved across hundreds of millions of years. They do not fade. They do not forget. They simply sit in the dark, waiting for someone with the right tools to read them. Scientists have been reading them, and what they show about Earth's rotation, its magnetic shield, and its deep interior is both calming and deeply serious at the same time. Some of the oldest records come from lava. When molten rock erupts and flows across the ground, it is liquid. As it cools and hardens, tiny crystals of magnetic minerals inside it turn to line up with Earth's magnetic field at that exact moment. They freeze in that direction as the rock solidifies, like millions of tiny compass needles locked in stone. Those frozen directions can last for billions of years. By collecting pieces of volcanic rock of many ages and measuring which way those tiny magnets point, scientists can rebuild the history of Earth's magnetic field. They can see when the field was strong and when it was weak. They can see where the magnetic poles were, and when they were in very different places than today. They can see each time the field flipped, when north became south and south became north. The clearest record of those flips sits on the floor of the oceans. New seafloor forms along mid-ocean ridges where lava leaks out and cools. As the lava hardens, it locks in the magnetic direction of that moment. Then more lava comes, cools, and locks in the new direction. Over millions of years, the seafloor moves outward on both sides of the ridge like a slow conveyor belt. The result is a pattern of stripes, one band with normal polarity, the next with reversed polarity, and so on. These stripes are perfectly mirrored on both sides of each ridge. They form a barcode of stone stretching across whole ocean basins. From this barcode, scientists can see not only full magnetic flips, but shorter, sharper events called geomagnetic excursions. During an excursion, the field weakens, the poles wander, but the flip does not fully complete. Then, the system pulls itself back into something like its old state. The best-known example is the Lashump excursion, about 42,000 years ago. Evidence shows that during Lashump, the global magnetic field dropped to maybe 20% of its usual strength for several hundred years. The poles drifted far from their normal positions. Then, over the next few thousand years, the field grew strong again and the poles moved back. We know this not only from rocks, but from ice and trees. Ice cores from Greenland and Antarctica, cave minerals, and very old tree rings all show the same story. With a weaker magnetic shield, more cosmic rays from space hit the upper air. That changed the chemistry of the atmosphere and increased certain rare radioactive atoms, which we can still measure today. Some regions show signs of ecological stress in that time, though life as a whole did not collapse. The point is not that another Lashump will happen tomorrow. It is that these events are real parts of Earth's normal behavior. And the way the magnetic field looks now, weakening overall with a growing South Atlantic anomaly, has similarities to the patterns seen in the rock record before past unstable periods. The rocks do not give dates, but they show that deep shifts in the field are possible, and they have happened before. The buried record also tells us about how fast Earth has spun. Coral is one of the most precise natural clocks we have. Coral reefs grow tiny layers day by day and thicker bands year by year. Under a microscope, you can count daily growth lines within each annual band. In corals that lived about 400 million years ago, scientists find around 400 daily lines in each yearly layer. Today we have about 365 days in a year. The year is set by the orbit around the Sun, so it has always had the same length. If there were more days in that same year long ago, each day must have been shorter. Those old corals tell us that back then, one day lasted about 21.5 hours. Earth was spinning faster. Over time, the pull of the moon on the oceans has acted like a brake, slowly making the days longer. Another kind of record, called tidal rhythmites, pushes this story back even further. These are rock layers formed from ancient tides in shallow seas. The repeating pattern of thin and thick layers carries information about how many tides and how many days there were in a year. Rhythmites from about 620 million years ago point today lengths of roughly 21 to 22 hours. Different records, same message. Over hundreds of millions of years, Earth has been slowing down. But that slowdown has not been perfectly smooth. Within the long trend, the rate has changed. There were times when the spin slowed more quickly and times when it slowed more gently. There were also shorter episodes when the spin actually sped up for a while. Shifts in the liquid core, giant volcanic periods, and the slow movement of continents all changed how the planet's mass was spread out, and with it, how fast Earth turned. The current acceleration is unusual when we look only at the last few decades. In the full span of geological time, temporary speed-ups are not unique. The rock record shows that the rotation can and does respond when the deep interior and the surface systems move together in certain ways. One of the best natural tests of this is the end of the last great ice age. From about 20,000 to 15,000 years ago, huge ice sheets over North America and northern Europe melted away. Kilometers of ice turned into water. That water flowed into the oceans and spread out. Land that had been pressed down by the weight of ice slowly rose back up. Sea level climbed by about 120 meters over several thousand years. Within that long rise, there were sudden jumps. The sharpest was a period called Meltwater Pulse 1A, roughly 14,500 years ago. During that short window of 3 to 5 centuries, sea level rose an extra 14 to 18 meters. That is an enormous amount of mass moving from high latitudes to the oceans in a very short geological time. Model studies suggest that this rapid shift changed Earth's rotation in ways large enough to detect. It also changed the stress on the crust. When ice melts, it removes weight from the land. The crust lifts, and the partly melted rock under it can more easily rise and erupt. Iceland shows this clearly. A volcanic activity there increased after the big ice sheets retreated, with a delay of a few hundred years as the crust adjusted. We expect similar effects now. Greenland is losing ice. Parts of Antarctica are thinning. Early measurements from Iceland, from the edges of Greenland, and from West Antarctica hint at subtle increases in underground pressure changes and small quakes. Signs that the crust is beginning to respond. Even if ice loss stopped today, some extra volcanic activity in these regions would likely continue for centuries, simply from the adjustment already set in motion. The deeper rock record points to another time when rotation, climate, and life were all under heavy stress. Between about 500 and 450 million years ago, Earth spun faster than it does today. During that span, the planet went through wild swings, deep global glaciations, then strong warming, then another freeze. Sea levels rose and fell. Ocean chemistry changed. Near the end of that era came the End-Ordovician mass extinction, which wiped out roughly 85% of marine species. Scientists link that disaster mainly to sudden climate shifts and sea level changes, not directly to rotation itself. But the timing lines up. The rocks show a world where the deep interior, the climate system, and the living surface were all in rapid motion at once. None of these ancient records give us a script for what will happen next. They cannot say which year something will occur, but they do define the range of what this planet can do. They show that magnetic fields can weaken far more than we have yet seen. They show that ice sheets can collapse faster than most models once thought. They show that rotation can change enough to matter for the systems that sit on top of it. They also point to a hard truth. The most dangerous time is rarely the calm after a big change. It is the time during the change itself, the transition, when old balances no longer hold, and new balances have not yet formed, when forces that used to cancel each other no longer do, when systems that once moved in step begin to fall out of rhythm. Taken together, the signals from the core, the oceans, the air, the ice, and the rocks all point in the same direction. Earth is not in a simple, steady state. It is moving from one pattern to another. We do not yet know exactly what the new pattern will be, but we are living through the crossing. The planet has survived many crossings before. Life in some form has endured every one. The difference now is that our systems, our power grids, our satellites, our cities, our food chains, are built on the quiet stability of the last few thousand years. The question is not whether Earth can handle the transition. It is whether we can understand it fast enough and clearly enough to adapt while the change is still underway. When scientists from many fields line up their results on the same timeline, a clear pattern appears. These scientists work in different countries. They use different tools. They look at different parts of Earth. Yet when they put their graphs side by side, many of the lines begin to bend away from normal in almost the same decade. That is the important point. The inner core data shows a change around 2009 to 2010. It looks like the inner core slowed down and began to drift the other way. Estimates of how the liquid outer core is moving, based on changes in the magnetic field, also show a shift in that same period. The length of the day at the surface starts to speed up clearly around 2016. The very shortest days ever measured arrive in 2020, 2021, and 2022. Greenland's ice loss speeds up around 2012 and keeps getting faster. The weakest part of the magnetic field, the South Atlantic Anomaly, starts to deepen more quickly in the mid-2000s. Arctic sea ice, which reflects how the air currents are changing, has its sharpest multi-year drop beginning around 2012. The Great Ocean Conveyor in the Atlantic, the AMOC, shows its fastest weakening in the mid-2000s as well. 7 different systems: the inner core, the outer core, the planet's spin, Greenland ice, the South Atlantic magnetic weak spot, Arctic ice and the jet stream, the Atlantic overturning current. All of them begin to act differently within roughly the same 10-year window, from about 2010 to 2020. Could this be pure chance? Yes, in theory, but the odds are low. The better explanation is that the Earth system as a whole has entered a new phase. A change deep inside, or high above, or both, has sent waves of change through many layers at once. It is as if someone tugged on one part of a spider web and the motion spread across the entire net. Scientists have built 3 main ideas to explain what might be happening. These ideas do not fight each other. All of them may be partly right, but each one gives a different picture of what the next few decades could look like. The first idea puts the solid inner core at the center of the story. In this picture, the inner core slowed down, then began to move slightly backward compared with the rest of the planet. When it slowed, it gave up some of its spin. Because spin must be conserved, that extra spin moved outward into the outer core, the mantle, and finally the surface. The result is that the crust and the oceans rotate a little faster. If this idea is right, the current speed up is like a wave of momentum moving upward. Once that wave has passed, and the inner core and outer layers reach a new balance, the acceleration should slow down or even reverse. The timescale for this could be several decades. The final change in day length might be about the same size as the change we are seeing now, but in the other direction. The second idea focuses on ice and air. Here, melting ice at the poles, especially in Greenland and Antarctica, changes how heat moves between the equator and the Arctic. That heat contrast controls the jet stream. As the contrast weakens, the jet stream slows down and becomes more wavy. Those changes in the high-altitude winds move large amounts of air mass around, and with it, atmospheric spin. Because the total spin of Earth plus air must stay the same, when the pattern of winds changes, the spin of the solid planet changes too. In this view, the core is still important, but it is not the main driver. The main driver is the way human-driven warming is reshaping ice, oceans, and air currents. If this is correct, so then, as long as we keep losing ice and warming the planet, the rotation changes could continue or even grow stronger. The third idea is more speculative, but still based on physics. It looks at the magnetic field and how it connects the liquid outer core to the rocky mantle above. Electric currents in the outer core create the magnetic field. That field, in turn, creates a kind of magnetic friction between the core and mantle. If the field weakens, and especially in places like the South Atlantic Anomaly, that friction changes. In this picture, a weaker field means the outer core can slide past the mantle more easily. Spin moves more freely from the core into the outer layers. The current acceleration would then be a sign that the magnetic field is moving toward an unstable phase, such as a strong excursion or the early steps of a future reversal. If this is right, the speed-up could continue until the magnetic field begins to recover, after which the rotation might swing back the other way. None of these three ideas has been fully proven. None has been ruled out. Papers have been written supporting each one. Other papers have raised doubts and offered other views. But all sides agree on one major point. This is not random noise. Something real is happening. The disagreement is not, is there a story here? But who is the main character in that story? Now think about what this means for us. Human civilization, as we know it, farming, cities, writing, industry, grew during the last 10,000 years. By Earth standards, this was a very calm time. The big ice sheets had already pulled back. Sea level rose and then settled. The magnetic field wobbled, but stayed fairly strong and stable. The length of the day changed only a tiny amount each century. We built our world on top of that stability. We built cities right at the edge of the sea, assuming the shoreline would barely move in a human lifetime. We built satellites and GPS systems, assuming Earth would spin in a very steady way. We built power grids and stock markets that depend on precise timing, assuming the global clock would not surprise us. We built navigation systems that assume the poles will drift only slowly. Now, those basic assumptions are under pressure. Sea level is rising faster. The ice sheets are melting in new ways. The poles are drifting faster. The magnetic field is weakening faster in some regions. The length of the day is changing in a way our systems did not expect. None of this is a disaster by itself, and it is not all happening in a single year. But together, they make life harder for systems that were tuned for a quieter planet. Engineers and scientists see this. They are already updating software, rewriting standards, and planning new rules for timekeeping and navigation. But change at the scale of global systems is slow. It needs money. It needs political agreement. It needs many different countries and industries to act together. As the rate of planetary change rises, the time we have to adjust shrinks. Here is a fair summary of what we know. The range of possible futures for Earth's behavior is wider now than it looked 20 years ago. More satellites, better clocks, and better models have shown us how many parts of the Earth system are connected. A change in the core changes the magnetic field. A change in the field changes how the core and mantle share spin. A change in ice changes sea level, the rotation axis, and ocean currents. A change in ocean currents feeds back into the air above them. These are not poetic links. They are physical links you can measure. Scientists use a word for systems like this: non-stationary. It means the rules are shifting. The averages, the typical ranges, the normal patterns are not fixed. They are sliding. When a system is non-stationary, you cannot safely assume that the future will look like the past. You have to expect new behavior. The rock record, from coral and lava and ancient sediments, tells us something else important. The most dangerous times are usually not the quiet states at the beginning or end. They are the in-between times, the transitions, times when balances that held for a long while are breaking and new balances have not yet formed. In such times, a small extra push can have a big effect. Surprises become more likely. All of this can feel heavy, so it is worth stepping back and looking at the longer story. Earth has been here for about 4.5 billion years. In that time, It has frozen over almost completely more than once. It has been struck by giant rocks from space. Its magnetic field has shut down and restarted. Its continents have crashed together and torn apart. Its oceans have turned to acid and then cleared again. Through all of that, the planet has kept turning. Life has been here for around 4 billion years. It has gone through at least 5 major mass extinctions and many smaller crises. Each time, most species died, but some survived. From those survivors, life spread and changed and filled the planet again, in new forms. Every plant, animal, and person alive today is the result of that long chain of survival. So yes, what is happening now is strange for human history, but it is not strange for Earth history. The planet is not broken. It is changing state, as it has many times before. For us, the risk is that we have built complex systems that assume the old state will last forever. We must take the risks seriously. We must measure, think, and adapt. But we do not need to fall into despair. Instead, we can choose a different response: attention and wonder. We can keep watching the core, the field, the ice, the oceans, the air. We can keep improving our models and our plans. We can remember, every so often, that we are standing on a living world. Deep below your feet, iron is flowing in the dark. It is powering a magnetic shield that turns deadly space radiation aside before it reaches you. The slow shift of that iron is adding or removing slivers of a millisecond from each day. In rocks and old corals, the planet has written a record of everything it has done. Its flips, its freezes, its storms, as its restarts. You live on something far older and more complex than it looks from where you stand. A moving, breathing planet. A planet whose spin is changing in tiny ways you will never feel directly, but which we can now see with instruments sharper than anything our ancestors could imagine. Let that idea sit with you for a moment. The Earth is turning beneath you right now, a little faster than before, a little differently than a generation ago. Far below, yet in heat and darkness, the iron core is still flowing. The magnetic field is still wrapping this world in its quiet protection. The satellites are still watching. The scientists are still listening. The planet has carried life through countless changes. It is carrying you now. You are part of this story. You are safe in this moment on an ancient spinning world that is still, always, finding its balance.